Awesome. So today I'm going to be talking about why matter is stable. And there's two basic levels.
Who are you?
No, what's your name?
My name is Chris Kacharzik. I'm a senior majoring in physics, minoring in computer science.
Where are you from?
I'm originally from Connecticut. Going there tonight at 11. And yeah, I'm lecturing on why matter is stable and like why we don't just like fall through shit and stuff.
Why wouldn't matter be just stable?
There's a lot of reasons why, and I will be talking about that as we go through the lecture. Basically, the first part is going to be a little bit more specific, and it's going to focus on why atoms in particular are stable and don't just collapse, right? Because you've got a proton and a neutron, you've got, a proton and an electron, you've got two things that are attracting one another. Why don't you just, combine and explode? The second part of the talk is going to focus very broadly, where I'm going to make broad sweeping generalizations about physics, about interatomic stuff, and in particular why things are about as dense as they are and not denser. Cool. So let's start right away talking about the stability of atoms. So for the most part, we've got this really classical notion of an atom, where you'll see most stuff drawn, where this guy's a proton, and then orbiting it around it in some sense, almost like a planet, you've got an electron. All right. This picture is wrong for a number of different reasons. The main one being you've got some potential, and the math stuff that I'm going to write you don't have to understand, but if you do, that's good. You've got some potential here, right? But the basic idea is that if these two are attracted, right, why doesn't the electron just fall into the nucleus and spiral inward or whatever? The first reason that you're usually given is it's angular momentum, right? The electron is like a planet in that it has some amount of angular momentum, and that centrifugal force going outward balances exactly with the force pulling it in. That's also wrong. Why is that also wrong? Because electrons, when they're orbiting in a circle, give off something called synchrotron radiation. And there's an entire building up at SLAC called the SSRL, the Stanford Synchrotron Radiation Laboratory, that is entirely devoted to using synchrotron radiation to look at things like biological proteins and other things like that. Not limited to the LCLS as well, which is also doing some really cool work anyway. So this synchrotron radiation would cause the electron to emit photons. And what would eventually happen is it would radiate away all of its energy, and it would eventually lose that kinetic energy, and it would still fall into the nucleus. So something is still wrong. Something is still very, very wrong.
So is that an electron and the floor is a proton?
Yeah, precisely. So something is still wrong with this picture. And it turns out that what's wrong with this picture is this idea that a proton and an electron are some well-defined particles in some form of an orbit, right? If you got anywhere in high school or college, chemistry or physics or whatever, you know that we have this concept of an electron cloud, which is basically that the electron exists in some not that well-defined cloud around the nucleus. And this picture is a little bit more accurate, right? And one of the reasons why it's a little bit more accurate is, let's say, barring everything else, that we were able to find the electron within some radius of the proton, right? If the electron were really falling into the center of the nucleus, we would be able to find it in some space around here. And we'll call this width right here, for obvious reasons, delta x, all right, where x is the distance and delta just stands for the change in distance, right? The main problem here is that we've got the Heisenberg uncertainty principle. So I shall state without proof that the Heisenberg uncertainty principle states that sigma x sigma p is greater than or equal to h bar over 2. This is some constant. Sigma x and sigma p represent the uncertainty in the position and the momentum of a particular really, really tiny particle. And so what this essentially says is that there's a really famous or a funny joke about the Heisenberg mobile, in that it's the worst car ever because as soon as you look at the speedometer, you have no idea where you are. What this equation basically says is that the more certain you are about a particle's position, the less certain you can be about their momentum, because this is the product of these two is bounded by this constant h bar over 2. Yeah.
Can that uncertainty be integers?
Yeah, but we're not really dealing with that right now, because in particular electrons and protons have a well-defined mass. There is an equivalent uncertainty principle called the energy time principle, which looks exactly the same, sigma E, sigma T, greater than or equal to h bar over 2. And that's where you get uncertainty in mass. Because for very short-lived particles at CERN, at SLAC, anywhere you have very massive particles, this concept of like a well-defined mass goes out the window, because whenever you measure stuff, you get this width, where you will actually measure the same particle to have a different mass multiple times. And that's why I should clarify that often people will not get confused, but will misinterpret the Heisenberg uncertainty principle to mean like, oh, like it's existing in 6 places at once or whatever. There are things called Bose-Einstein condensates, which are these macroscopic quantum objects that do exhibit some really interesting quantum effects, like seeming or appearing to be in multiple places at once. That's a totally different story, but what the uncertainty principle and what quantum mechanics really boils down to is that there's some ambiguous probability distribution for a given particle, and that when you measure it, it will have a well-defined position, but until you measure it, you're not exactly sure about where it is, so it can be in any one of a number of different places. Particles are described by wave functions. If you've ever seen like this thing, that is the usual symbol for what a wave function is. There's a number of different things. We'll get into that actually a little bit later on. So you can have multiple different uncertainty principles. The generalized uncertainty principles, for those of you following along at home, is sigma A squared sigma B squared is greater than or equal to 1 over 2I times the expected value of the commutator of A hat and B hat, where A hat and B hat are quantum mechanical operators. You can basically substitute anything there, any of the momentum operators, stuff. Amy's smiling because she has probably done this before. But this is basically, so for the energy time uncertainty principle, you would put the Hamiltonian operator, which is what gives you back energy, and the time operator, just the partial derivative with respect to time. And that's what would give you this relationship right here. Similarly, you would put in x hat and then the quantum mechanical equivalent of the momentum operator, and that's what will give you the Heisenberg uncertainty principle as it's known today. One of the things you learn in quantum mechanics, real briefly, is that every physical quantity that you can measure has associated with it some mathematical operator that gives you back values, or possible values for that measurement. But that's a totally different story, and we're not going to go into that right now. So going back to this picture of the atom, right, we had this totally unclear. So this is the proton, and we have this circle of, diameter or radius or whatever, delta x. What does that mean? And the Heisenberg uncertainty principle says that the closer we bound the electron to the nucleus, the more uncertain we are about the possible values for its momentum. So in other words, the closer the electron is bounded to the nucleus, the faster it can be traveling. Which means that if we try to squeeze this in more and more, all that means is it's going to be traveling much more quickly in totally different directions. And the happy medium comes when you solve completely for the hydrogen atom, which is the only atom that we can actually solve for completely using what we know about quantum mechanics. And I'll write down some of that wave function stuff here. Quickly erase. Any questions?
Could the momentum also be really small? I thought that you don't know the momentum, not that it's fast.
It could be really small. The problem is that you don't know it, right? The problem being that, like, yeah, if you were to theoretically measure the momentum for a bounded thing, it could be really small. It could also be very, very large, and that's going to naturally lead to a much larger distribution. One of the most famous examples illustrating the Heisenberg uncertainty principle is the idea of like a microscope, right? Let's say you wanted to measure exactly where an electron is. When you have a microscope, you're sending in light, you're bouncing it back so that it hits your eye. If you're trying to measure where an electron is, you're bouncing a photon off of it, which is giving it a completely new momentum and hence a completely new position, right? And that when that photon hits your eye, you know exactly where it is, but now you have no idea how quickly it's going, hence where it's going to go next. Is that?
That's not what I'm saying. I understand that when we know, so you bounded, we know pretty specifically where the position is. That's like we don't know what the momentum is. Like the more specific we know the position, the less we know about the momentum. That doesn't mean that it's going fast. You were saying that it could be going really fast. I was saying it could be going really slow.
It could be, right?
So why isn't it? I'm saying there's no reason to think that it's going so fast. Never mind.
But it could be, right? Like we have no idea.
I think what you had said was the more you had said one thing, and then you also said that we know that as you get closer to the proton, it's moving faster.
Exactly.
How do we know that?
Because the electron is dictated by a potential, right? That Coulomb interaction. Is everyone familiar with like basic electro stuff, right? Like positive negative charge goes as 1/r². Because it's dictated by the potential. Because as it gets closer to the nucleus, it has to be traveling faster to conserve energy. Right? That's a totally different idea. What?
Planet orbiting is a way to think of it.
Yeah, a planet orbiting is a way to think about it, right? As you have something falling down to the Earth, it's going faster and faster and faster. It's not the best way to think about it still, because you can actually show in quantum mechanics that there's a non-zero probability that you'll actually find the electron inside of the nucleus. But that's a story for a different time. Yeah.
So I just wanted you to clarify a little bit. So you're saying, well, your uncertainty varies depending on what you're trying to measure, right? But you would say, well, innately it might have some uncertainty, and so I wanted you to sort of like parse the. So like you would say, well, the wave function collapses as soon as you try to measure it. Right?
Yeah.
But innately, so like you could imagine, like the electron has some position and some momentum. Is it uncertain in its own momentum and position, or is it only uncertain when we try to measure it and we see that uncertainty?
So I would ask, why does it matter which one is which, right? Because if we can't measure it, this goes back to the idea of quantum entanglement, right? Until we measure two entangled particles, we have no idea which one is which. Right? This is a very like Schrodinger's cat argument, right? We have this box, we have a cat that we don't know whether it's alive or dead, right? So it exists in some superposition of the two states. The cat knows whether it's alive or dead, but it's already observed and collapsed the wave function, right? Whereas we're outside this box and we don't know which one it is, so it exists on some continuum. It exists on some probability. So yeah, the electron knows in some sense, but it doesn't matter until we measure it. Okay, so going back to the hydrogen atom, we talked about how it doesn't fall into the nucleus because that would mean that we can contain it in some way, and that will lead to big uncertainty in its momentum. Turns out we can actually solve exactly what the hydrogen atom wave function looks like, and I'm going to write it down because it's kind of important for one little piece at the end, but it's going to take me a little while to do so. Okay, so this is equal to, sorry, this is a function of rho, which is the radius, theta, which this is in spherical coordinates, and again, this is just for those of you following along at home. This is 2 over that. Sorry, this is just some constant. It's minus all this. 1. This is factorial over 2n times n plus l factorial exponential minus rho over 2 rho l.
This is just a trivial solution.
L. I mean, this is the only one that we actually know how to solve for. Okay. This is rho times.
Charlie, I was going to make a joke,
Okay.
but I think yours was.
So these are the Legendre polynomials, which are this is an entirely different set of equations, and these are the spherical harmonics, which is another entirely different set of equations, right? But by writing this down, what I basically wanted to get at is hopefully you can see visually there's a radial portion to this equation, and then there's something that only depends on the angle. And this is where the quantum mechanical notion of spin comes from. You've probably all heard about spin in one form or another, and the fact that this angular portion is separable from the rest of the equation is one of the things that allows us to solve it in the first place, and one of the things that gives rise to this notion of quantum mechanical spin. It's a little bit more complicated than that. It has to do with angular momentum and angular momentum operators in particular, but we're not going to go into that. And then the energy for the nth energy level is equal to some constant energy over n squared, and the energy for the hydrogen atom is negative. Okay, So for now let's expand beyond the notion of just the basic hydrogen atom into atoms that we